There we go. Sorry, thought I unchecked it. Preview question 45. All right, so you're trying to classify these compounds as that's weird. It's like it's already listed them for me. So on my end, it's actually just giving me the solution. I don't know why it's not even asking me the problem. So you're given a class of compounds and you're trying to determine if the compounds are ortho-meta activators, ortho-para directors, or meta deactivators. So your ortho-para here, this is going to be if you have a lone pair on the bridge atom, on the bridging atom. So let's say we're going to make X our bridging atom here. And potentially there is an R connected off of it. So wow, this is actually really confusing. So generally speaking, if you have lone pairs, you're going to have it's going to be an ortho-pair interaction. Activating and deactivating here is also going to be one of those. Okay, so the other thing is also activating versus deactivating. Typically, if you're an activating branch off a benzene ring, you're also an ortho-para director. So if you go through your tables and you look up what are activating groups, those are all ortho-para. The reason why I'm saying the question is kind of weird, it talks about these ortho-para deactivators. The activators here are actually kind of a debatable thing. Activators. They're all going to be your halogens. So the reason why I say this is debated, Francis Carey has actually changed between editions saying what they do. I've also looked online, I've gone to other resources, and there's kind of this debate in the literature about whether or not halogens are activating and deactivating. Everyone says that they are mild, but they don't really specify, like, I've seen people claim that they're deactivators, but they claim they're mildly deactivating. I've seen group books say that they're activating, they're mildly deactivating. The honest answer is that they are ortho-para directors because of the lone pairs, but whether they're activating or deactivating, I would argue it's probably more deactivating for fluorine versus something big like bromine or iodine. But on a whole, you're not going to see much of an effect due to halogens. But definitely for your activating groups, any hydrocarbon or any alkyl branch, so anything that contains just carbon and hydrogen, and anything containing a lone pair on the bridging atom, those are going to be your ortho-para activators. Your meta deactivators, pretty much anything where the bridging atom is bound to something that's more electronegative than that bridging atom. So one of the examples is a nitro group. Nitrogen does have lone pairs on it. Well, okay, the nitro NO2 group doesn't actually have lone pairs on the nitrogen, but some people do draw it that way. But definitely those oxygens being bound to that nitrogen make it deactivating. Something like a cyano group, that's CN, that makes it a deactivator because the nitrogen is more electronegative than carbon. Alcohols, or I'm sorry, sulfoxide groups, aldehydes, ketones, carboxylic acids. These are all meta directors. They're also deactivating. So anything that is a deactivator is going to be a meta director. We don't have any meta activators. So again, it's kind of weird on my end because it's showing the solution. It's not showing, it kind of shows me what you would have seen. But anything that is an activating group automatically goes into an orthopara director. The only deactivating orthoparas, according to this version of the book, are the halogens. Again, you can find books that argue both ways. I would honestly say that the halogens doesn't activate or deactivate, or if they do, fluorine's deactivating. Something like bromine's, iodine's probably activating. The reason why they're orthopara directors is simply because of those lone pairs. And then anything that is deactivating, so that bridging atom between the benzene ring and whatever's bound, whatever's bound to it. Anytime that you have an element, that bridging atom bound to something that's more electronegative than that element, those are going to be deactivators, and they're all going to be meta. So hopefully that answered your question. And that was kind of a prattling explanation. You're welcome. Other questions? Come on, I got 4 concurrent viewers. Some of you had to have questions. So carboxylic acid, COOH, those are always meta directors because they're deactivating. You're welcome. Do homework 5. Homework 45 for test 1 material organic 1. Right, bring that up. So assign the chemical shifts to the appropriate positions of para-nitrophenyl propanoic acid. So let me draw up. So there is a table on the course website under test 1 which will give you a list of the common chemical shifts. But some of these we can tweeze out pretty quick. So it gives you the chemical shifts. Wow, that is obnoxious. It's doing it reverse. 1.6, 4.0, 7.5, 8.2, and 12.0. Write that so you can actually see it. So in general, this is basically making sure that you can use a table and understand how the tables work. So I would recommend you go to the course website under, I think it's under lessons as well as underneath the test material. You can find tables of common NMR shifts. The big thing is that you get more D-shielded the more electronegative elements you're bound to. So E should be the easiest one. Is on a carboxylic acid. It's bound directly to hydrogen. So E is definitely going to be the 12.0 ppm. Now, in your tables of common ranges, you're going to find that alkanes sit in the 0.5 to 2.5 range. The further we get away from the electronegative elements, the better the chemical, the more shielded it's going to be. So B here is going to be the 1.6. A is going to be the 4.0. Now, if you look up in that table, you're also going to see that chemical shifts of aromatic compounds like arenes, benzenes, things like that, those are much more down in this region. When you take organic 2, we'll talk about where this effect comes from. Again, we're going to look at how far we are away from electronegative elements. C is closest to the nitrogen, so C here is going to have the shift to 8.2, and D is going to have the shift to 7.5. So let me check my work. E, B, A, D, and C. And that's correct. So it's BADCE. Again, the line of reason being that if you're directly bound to a super electronegative element, particularly something like carboxylic acid, you're definitely going to be completely de-shielded. So alcohols sit about 9 because of the hydrogen bonding. Carboxylic acid even further down. Alkane groups, these all sit in the high region, and we're going to rank them based on who's closest to this carboxylic acid, who's closest to the oxygen. Again, if you look up in the tables of common NMR shifts, you'll see that this is a typical range, and we're going by who's closest to the most electronegative elements. So since C is closer, it's more de-shielded. D is furthest away, so it's the more shielded. Hey, you're welcome. There we go. Which pages in the study package should we be able to complete at this point for Orgo 2? Oh, thank you for the playing. Complimenting the playing. Alright, let me actually download the packets and see what's on there. There we go. Bring me back to that web page. Still loading. And of course I was in the wrong course shop. Hold on. Almost there, Elijah. It's definitely page 1. Keep going. Page 2. The review material, so reviews or reactions of alkenes. Alkenes. Reactions of allylic hydrogens, you should definitely be able to do. Reactions of polyenes. Diels-Alder is actually a review from Organic 1, so you should be able to do that as well. Naming the benzene derivatives. So I would say you should be able to go through about page 20 at this point, and then reactions of benzenes and directing groups and the hard syntheses, reactions with characterization, that'll be due next week. You're welcome. Can we go over number 52 in the Organic 2 homework? Sure. Make sure I'm in the correct course shell. Choose the best option for the enzymatic precursor to the target molecule. Okay. So the target molecule here is this molecule here. So bromo, nitro, trifluoromethyl. So the thing is, all of these are meta. So because they're meta, ideally we'd have whatever we pulled off before would be added in the meta position. So we actually have two meta directors here. We've got this one and this one, and technically this one. But so synthesis of 1 bromo, 3 nitro, 5 trifluoromethylbenzene from benzene. So we're going to start with benzene. Now, another thing to keep in mind, so technically by the book's definition, all three of these are meta directors. So if we're going to go with their definition, then we're going to, since we're adding meta directors are all electron withdrawing. So what we don't want to do is add, we don't want to add the nitro group first because it's going to slow down the reaction. So practically nitro is going to be the last one we want to add first. So my first guess is to say that we're going to add the nitro group after the fact. So I would say this is probably your precursor, and we're going to nitrate it with the aqua regia. So let's see if I'm right. And again, the reasoning here is that all three of these are meta directors, so it doesn't really matter. I don't have to worry about which ones I add first in terms of which way the reaction is going to go. But I would definitely say that the nitro group is strongly deactivating, so we want to add that as a last step. And it tells me I'm wrong for some reason. What? You just said it's a meta director. Okay, well, obviously they, all right. So according to them, bromine is not a meta director. So we're going to have to add the bromine last then. So we'll have AlBr3 and Br2. Okay, so that's correct. Now, where do we go from here? Well, I conceptually don't know a way to produce that without a lot of weirdly weird reactions. So the precursor here to the meta nitrofluorobenzene is going to be one where the nitro groups get added, because we can definitely do this in a single step. If we add nitric acid, HNO3, and sulfuric acid, which we'll be doing in a few labs, we can definitely get back to the CF4. So if I do the nitro in one step, see if that's correct. That's correct. All right, so we got the CF3. What's the next part of the question? So choose the appropriate agents for the conversion of trifluoromethylbenzene to M-nitrofluorobenzene. So I've already actually given you this answer. To convert this to this, CF3, you're just going to work with the HNO3 H2SO4. And then to convert the para-trifluoromethyl nitro to the final compound, you're going to work with AlBO3 and Br2. That is not an... Oh, yeah. It's using FeBr3. These will both accomplish the same thing. That's apparently it. It's a good synthesis. But yeah, so my line of reasoning is that we ideally, depends on what book you consult, definitely CF3 and NO2 are going to be meta directors. So if you're looking for the step back, since they both direct to the same group, honestly, if you think all three of these directors, I would say add the nitro latch just because it's deactivating, but since it considers the bromo ortho-para director, we'd add the bromine last. And you would do that with FeBr3 or AlBr3 and Br2. Before that, you would do the nitro group because that can be accomplished in a single step. Odds are what you're starting with is toluene. And I would assume before that, you're just doing a lot of free radical halogenation with fluorine. That would be a terrible synthesis to run. You're welcome. This week's Orgo 2 discussion boards are the number of points for each question and hint about the answers. Yeah. Make my grading a lot easier. Yes. So that's kind of like what it's there for. And to make my life easier, so. And that's going to be true for all the discussion boards. If you notice, like, there's an oddly specific number of points assigned to, so definitely for the last discussion board with the halogenation one, I told you, like, there's one, each of them are worth 1 point except for the one that's worth two, and one of them produces more than one product, so it's probably the one that's worth 2 points. So if we draw these with the orbitals, would we be have anything hanging out the rings? All right, let me take a look at the discussion board before I answer that question. So traditionally with let me get my mind like that. Traditionally, when we think of the pi orbitals and the aromatic rings on aromatic compounds, we more think about them just hovering above and below the ring than we do about them hanging off the ring. They they actually do hang slightly off the ring. So for aromatic compounds, we're going to have electron density sitting above and below. So you can kind of think of it as its shape. It's going to look a lot like a burr. So the benzene ring is your patty, and then the bun above and below, that's the electron density and the aromatic components of the ring. So yeah, it does kind of like bulge off the edges a little bit, but generally speaking, most electron density is located above and below the ring. So that's point. So the point of this exercise is getting you to see where the aromatic parts of the molecule is. So it's we start simple by giving you a benzene ring where the whole thing's aromatic, but compounds are aromatic, but not necessarily the whole molecules are aromatic. So definitely, if you don't, just because you see things hanging off the ring, there, if things are hanging off a ring, they don't really count towards that ring or count towards your aromatic system. So if we look at something like benzene versus like a massive alkyl benzene, this is an aromatic compound because of this part, and then this is still aromatic. It's got an aromatic component to it, but not the whole thing's aromatic. But it's still aromatic. It's just not the whole thing's aromatic anymore. And I agree with you. I think that's part of the confusion, particularly because your book does the same thing where it says this is aromatic, and then it gives you examples that look nothing like the examples you worked on. So that'd be something good to add to the notes probably next semester. So it's also kind of akin to polarity. So you look at something like soap. Soap has a polar end and a nonpolar end. So is soap polar or nonpolar? Aromatic's kind of the same way. For simple molecules, you have this binary. It's polar or nonpolar, or it's aromatic or it's not aromatic. For more complicated molecules, it will be aromatic, but the whole thing won't be aromatic. It'll just be an aspect of it that's aromatic. But we would still consider the compound aromatic because it has the aromatic ring in it. You're welcome. And we're kind of at the end of the live stream. So again, if you have any questions, feel free to email them in advance. If you can't make the live streams, homework's free discussion, especially those of you in Orgo 1. We can talk about the modeling stuff that you're doing that's due next week. Also keep in mind their exams open up next week. You'll have all of next week plus the weekend to do it. But do make sure you do that exam. It'll be on Connect and free to answer any questions you have regarding test procedures. But again, I'm not going to answer test questions for you. All right. Thanks for showing up, and I will see some of you tomorrow in person and hopefully some of you tomorrow during the live stream.